Good morning. Another type of double replacement reaction that we can look at is called an acid-base reaction. Now, we've looked at double replacement reactions. Ultimately, the last reaction type we looked at was something called precipitation. And now I want to take a minute and look at another kind of double replacement, also known as acid-base. Now, you probably know a little bit about the idea of acids and bases and what they are. Maybe you learned a little bit in elementary school or middle school, maybe a little bit in chemistry or even biology. But just to kind of go through an acid-base reaction, an acid-base reaction is simply a reaction that forms salt and water. So to give you kind of an idea of what that would look like, it looks something like this. What makes an acid ultimately the acid is that it contains hydrogen, then the base contains hydroxide, and you think about that hydrogen and that hydroxide together, and what does that really make? Well, it just makes water. But in terms of understanding where the other product comes from, that is the salt, you've got to picture what actually an acid would be made up of or a base would be made up of. For example, let's just take a reaction such as this. NaOH plus HCl yields NaCl plus H2O. Those are two reactants, obviously compounds, producing two products that are also compounds. As we look at them, we see a few things. First of all, notice that in our reactants, notice we see the hydroxide, right, which was, as we said, means that that's a base. We see the hydrogen, which, as we said, means we're talking about something called an acid reacting, and notice what their two products are. Notice one of them was water, but then notice what the other one was, right? It was a combination of those two ions that were attached to the hydrogen and hydroxide. So it was a combination of that sodium ion, and that chlorine ion coming together to make, well, what's it called? It's called a salt, right? So that's generally what we talk about in terms of an acid-base reaction. Now, an acid-base reaction is very similar to a precipitation reaction in that we could technically do a net ionic equation from it. For example, you think about the NaCl, and the NaCl we know is aqueous. And in many cases, the salt that's produced will be an aqueous substance. But then we've got the water, and the water's not. The water's not aqueous. The water itself is a liquid, right? You have liquid water that can be added to things like solids and make the solids aqueous. But remember that the very act of being aqueous means that it dissolves into water, right? So it dissolves into the water. So you can't say the water's aqueous because the water is itself, right? It doesn't dissolve into itself. It is simply a liquid. So from that, you could picture that, you could technically write a net ionic equation in which you said that the hydroxide and the hydrogen simply produce what? They produce liquid water. Now, notice it's not a precipitation reaction because you're not producing a solid, but it is still a net ionic equation because you're getting rid of those spectator ions and you're being left with what produces the liquid water. All right, one more example could be as simple as ammonium hydroxide and H2SO4. Now, H2SO4 is called sulfuric acid. In just a minute, we're going to look at naming, and I'll talk to you about why or how you might know, how to name them. I know a few of you already have an idea, and we have talked about it a little bit over the summer, but if you're looking at this, same idea, right? So notice double replacement reaction. Notice you've got the hydroxide. Notice you've got the hydrogen, and they're simply doing what? They're coming together to make the water. But then what else happens, right? So if the ammonium and the hydrogen switch places, well, now notice you've got ammonium sulfate. Again, ammonium sulfate, based on our solubility rules, ammonium being one of those from Rule 1, meaning that it's got to be aqueous, so you've got aqueous ammonium sulfate and liquid water. So again, same idea. You could write a net ionic equation if you needed to for that reaction as well. Now, you were asked to take some notes over these basic reactions, and so hopefully you've taken these notes, just some basic ideas of what it means to be an acid and a base. And I'm just going to kind of move my way through these because you should already have these. These were part of an assignment that was already given to you. But let's just take a look at this slide really quickly and just kind of reiterate what I just said, because generally speaking, if we're talking about an acid-base reaction, if we have both an acid and a base, one of the most common names we'll use for this kind of reaction is going to be neutralization. Now you think of to neutralize, and what does that simply mean? Well, it simply would mean the taking of an acid and neutralizing it by adding a base, or vice versa, right? So the taking of something that's basic and causing it to become neutral by adding an acid. Now, to be neutral simply means to have equal amounts. So to be neutral simply means to have equal amounts of hydrogen and hydroxide. And the closer something is to neutral, so in terms of understanding this, the closer something is to neutral, the closer it will be to what we call a pH of 7. Now, I don't entirely expect you to know fully what that pH of 7 means, but you've probably heard that phrase before, because, for example, if any of you have a pool, you might know that anytime, you get your pool ready for the summer, or, you had a lot of people over at your pool, and so you want to check and make sure your pool is okay to swim in, one of the things you do is you measure your pool's pH. And the idea would be is that the pool's pH, you want it to be as close to 7 as possible. Why? Because if you think about it, if you've got equal amounts of hydrogen and hydroxide, well, that means that really what you have is just water, right? You have as much or as close to being just pure water as it can be. Now, what starts to happen in something like your pool is that as bodies are added to it and other things are added to it, that the pH will start to go up, and then it'll start to rise. And as that pH rises, what you'll actually start to find is that your pool will start to actually gather bacteria, and you'll start to notice that the water will start to feel slippery, and you might even notice a smell to it, and that just simply means that your pH is getting too high. So again, the idea would be is that as you neutralize two things, you're simply bringing a hydrogen and a hydroxide together, and you're making water. Again, reiterates what we just said. Hydrochloric acid, sodium hydroxide really just makes what? It makes water and sodium chloride. Again, through what kind of reaction? Well, a double replacement, right, where we see the sodium and the hydrogen switching places. All right, so we can continue on, and we can notice, just take, for example, a few different reactions, and as we look at these, we might, question, is it just the acid? Is it a base? Is it a neutralization reaction? And the key is that with neutralization, it's got to have both that acid and that base. So, for example, as you look down through these, notice the difference. Notice that, like with this first one, where you've only got hydrogen, there is no hydroxide. Well, this is just simply the production of an acid, right? So it simply is an acid. Whereas the next one, notice you've got ammonium and water. Again, you don't really have an acid. So what do you've got? You have a base. Notice that you've got that hydroxide that's given off. But then notice with the third one. Notice the third one, now you've got two compounds in which you've got both an acid, something that contains hydrogen, and a base, hydroxide, and that's how we know it's a neutralization reaction. Alright, we're going to go ahead and move on to the next couple slides and give you an idea of naming as well as how we're going to look at these in reaction sense. Alright, again, you have these notes, they're all in front of you, and we'll go back and we'll reiterate some more as we really get into acids, but let's focus for just a minute on the naming aspect, mostly because as we talk about these acids and we talk about these bases can be really easy to figure out, because all we have is just a hydroxide, and so there's no real new fancy naming system. But with acids, because sometimes we've got acids attached to just elements, sometimes we've got acids attached to hydrogens attached to polyatomic ions, because those hydrogen ions, which are positive, can attach to a lot of different things. We've got to have a special naming system for them. So, in order to understand this special naming system, let's start with remembering or reviewing that an acid is a substance that yields hydrogen, which means that whatever the acid is, whether it's something like, HCl, or whether it's H2CO3, or, HClO, or whatever it might be, that if we were to picture what is inside of this actual substance, that really it's just hydrogen and some other ion, right? Like hydrogen and chlorine, or hydrogen and carbonate, or hydrogen and hypochlorite. So in terms of naming, what we really got to understand is that since hydrogen is produced in all of them, the thing that might be different would be that other ion. It could be that that other ion is just simply an element, right? That other ion is just simply an element that is produced. And we can name it based on that. Or it could be that that other ion is what we call a polyatomic ion. And the name that we use to describe those polyatomic ions, and you'll find this in your textbook in a couple different ways, is you'll either call them oxyanions or oxoanions, and it simply means the same thing. Now picture that word, oxy or oxo. Ox really just meaning something attached to oxygen. You might even remember from Chemistry 1 that you learned that that's where that whole idea of polyatomic ions comes from. Like, for example, we know that these elements like carbon and nitrogen and sulfur and chlorine and phosphorus, well, we know that they can do a variety of things, right? Like, for example, we could take and we could talk about nitrogen, and we know that nitrogen could form just an ion by itself, but we know that it also could form some various oxoanions like nitrate or nitrite. We could also do something like that with sulfur, right? So we could have sulfur by itself, or we know that sulfur could form something like sulfate or sulfite. And we could keep going on, right? We could talk about chlorine. Chlorine's even more unique because we know that chlorine can form just the chloride, but then chlorine can actually form a variety. It can form perchlorate, it can form chlorate, chlorite, and even hypochlorite, right? So all these ions, again, we could define as just being an ion, or being what we call an oxoanion, which means a polyatomic ion attached to hydrogen. So then in terms of naming, we have to look at them based on that. So let's just take a look. For example, if we were talking about naming, simply put, it's like this. The addition of oxygen to the ic acid will produce a prefix such as per and a suffix as ic. Now I want you to picture what that means. So in order to do that, let's talk about a compound such as, let's talk about the chlorate ion. Now this is chlorate. Now when chlorate attaches to hydrogen and becomes HClO3, it becomes what we call chloric acid. What makes it an acid is that hydrogen. But now this tells us that the addition of an oxygen to that acid will produce the prefix per and the suffix ic. So let's think about that for a minute, because if this is chlorate, we could also have perchlorate, right, which is ClO4 negative. So if we were going to try to name that, well, what would it look like? If it were to become an acid, it would become HClO4. So we now take that perchlorate and it now becomes perchloric acid. But what if we were to go in the other direction? So if this is chlorate and this is perchlorate, what if we were to remove one of those oxygens and instead we had what we should hopefully know as chlorite? What would it look like now? Well, when we remove an oxygen, that ic now becomes us. So if we now have chlorite as an acid, HClO2, that chlorite now becomes chlorus acid. Now bear with me for just a minute because I want to look at one more and then we'll put it all together and we'll see an organization. So let's just look at one more. Let's say instead of just removing one of those oxygens, what if there was now another one removed? Now again, this doesn't happen with all of our compounds, right? We know that some polyatomic ions, they just become ite. They don't actually become like a hypochlorite. But we know that ClO negative exists, right? And that it's called a hypochlorite. So the question is, what happens to it when it gets hydrogen? What happens to it when it becomes an acid? Well, now that chlorous acid becomes hypochlorous acid. Now, these are the max that you're going to see. In other words, in terms of understanding what we would have if we were trying to name an acid that would be a polyatomic ion, such as chlorate, perchlorate, chlorite, hypochlorite, this is it. There's no other naming system as we add one more oxygen or we lose one more oxygen, because this is it. These are the only kinds of oxyanions we're going to see. But let's just organize it. So let's just picture. These are what we just talked about, right? So if we were looking at the oxoanion and seeing what its acid looks like, right? So what happens when it adds hydrogen, notice what happened. Perchlorate became perchloric, right? Chlorate became chloric. Chlorite became chlorus. And hypochlorite became hypochlorus. Now I'm going to add one more in, and that is, what if it's just the element itself? So we see all these, what happens when chlorine attaches with oxygen and it becomes an acid. But what if it was just chlorine, which is really just chloride? And this is one that many of you probably already know. But when it becomes just the element, it becomes hydrochloric, or hydro whatever that element is. So HCl, you might know, is hydrochloric acid. So let's do a couple, and then I'm going to do the first one with you, and then I'm going to have you do a few on your own. But let's just start with nitrogen. So let's say for number one, nitrogen was our anion, and we were trying to figure out some different ways to name it. So let's just start with nitrogen as an ion is in -3. So what if nitrogen as an ion bonded with hydrogen, right? We would get H3N. How would we name that? Well, because it's just elemental, we would say hydronitric acid. Now let's do the oxoanions. So let's just start with the 8. Nitrate is NO3 -1. What happens when nitrate attaches to hydrogen? It becomes HNO3. And based on our rules, If it's an 8, we call it what? 8s are ic. So, nitric acid. Alright, so what if that nitrate became nitrite? NO2, -1. Again, we have HNO2. And that ic became what? It became us, right? Ites are us. So 8s are ic, ites are us. Nitrous acid. And since nitrogen only has nitrate and nitrite, we could stop there. There is no per-nitrate or there is no hyponitrous. Alright. Alright, so let's do phosphorus. So that was nitric and nitrate. I'm sorry, and nitrite. What if we did phosphorus? So let's just start with elemental phosphorus, P-3, which means it would be H3P. And based on our rules, it would be called hydrophosphorus. I ran out of room. Acid. Alright, so let's start with phosphate. PO4, -3. Remember, 8s become ic. So it would be phosphoric acid. Alright, what about phosphite? PO3, -3. So again, it would be H3PO3. And phosphite becomes phosphorus acid. And then again, just like with nitrogen, we can't go any further, right? Because we simply do not have phosphorus or a per-phosphoric. Alright, let's do manganese. Now, manganese does have a variety of oxoanions. So if we were going to look at manganese, talking about elemental manganese can be a variety of things, and you think about manganese is actually a positively charged ion. So the only way you're going to see this manganese is going to be in oxoanion form. You're not going to see it as elemental, okay? So let's just talk about the different manganese ions that we could have. I'll go ahead and get rid of this. Now, manganese is not like chlorine in that it does not have all of the oxoanions, but it does have some. So, for example, we do have permanganate, which is MnO4 negative. So that's permanganate. We also have manganate, which is MnO3 negative. And we could say, for the sake of understanding, we could call this manganite. We really don't see manganite, but for the sake of understanding, we could at least call and say that if it was manganite, that's what it would look like. Alright, so let's go ahead and let's see what would happen when these things attach to hydrogen. So let's just start with permanganate. So permanganate would become HMNO4. And based on our rules, we would call it what? We would keep the per, but that 8 would become ic, right? 8s are ic, so permanganic acid. Alright, manganate would become HNO3, and that would become manganic acid. Alright, manganite. Again, we really don't see it, but let's just say for the sake of understanding we did. We would call that manganese acid. And that would be it. I encourage you to go back and look at your summer assignment at some of the acids that you were given. You had been asked to look at some acids and name them as part of your summer assignment in the naming compounds section. And I didn't necessarily test you on it, or if you were given a question on it on the test in terms of naming, I let you name it just regular, just calling it like hydrogen chloride or something like that. So I didn't really stress about how you did the naming with the acids for your Unit 1 exam, but I encourage you to go back and look at them and familiarize yourself, make sure you feel comfortable with them. If you do not, I encourage you to ask questions, come in if you're not sure about something, and we'll go from there. Alright, but let's just take that idea and let's say we were asked specifically to do some precipitation reactions with some different substances. So let's just take the first one, for example. Now, again, these are still precipitation reactions. It's just we're not actually producing a solid. These reactions are going to produce something else, like a liquid or even possibly a gas. We're not going to see gases in these reactions per se, but they're going to produce something other than that solid that we've been looking at. So let's just start with the first one. It says sodium hydroxide is mixed with phosphoric acid. And now that we have an idea of what that means when we say phosphoric acid, let's go ahead and let's figure out what this reaction would look like. So let's just start sodium hydroxide, which is really just NaOH, and it's aqueous, right? Because going back to that very first slide, anything that is an acid-base reaction, just like with precipitation, it's got to be an aqueous solution. So we've got aqueous sodium hydroxide, and it says it's mixed with phosphoric acid. So we've got aqueous phosphoric acid. Now remember, phosphoric, ates are ic, right? So if there's ic, then it's got to be an 8, so phosphate, so H3PO4. Alright, and it's reacting, right? Now, because it's an acid-base reaction, how do we know? Because of the hydroxide and the hydrogen. It's also double replacement, right? So we've got sodium and hydrogen switching places. So we know one of those products has to be water, so H2O, which again, remember, is a liquid. The other product has got to be sodium and phosphate, so it's going to be Na3PO4. Remember, sodium is one of those Rule 1 ions, which means it's always aqueous. So there is our reaction. Now the question is, what would an ionic equation look like for it? So let's go ahead and write that out. So if we were going to take this and we were going to turn it into an ionic equation, well, we would say something like this, right? So let's make sure it's balanced. We've got 3 NaOHs, and let's do 3 right there, and that should balance it out. Alright, so what do we got? We got 3 Na plus 1, which is aqueous, plus 3 OHs minus 1 plus 3 H's plus our phosphate yields 6. I'm sorry, you can't separate that. Go back. Yields 3 H2Os. Again, you can't separate it because it's a liquid, right? So it's not aqueous. It cannot be put into ions. But plus 3 NAs can be separated because it's aqueous, plus 1 phosphate. Alright, so let's look at what our spectators are, right? So our spectators, notice we've got sodium ions on both sides. Notice we've got phosphate ions on both sides. So really all we have left is the production of water, right? We've got 3 OHs plus 3 H's yields 3 H2Os. We could technically reduce that, right? So we could technically say OH plus H positive yields 3 H2Os, and that would be fine as well. But otherwise, we have our net ionic equation. Again, remember that generally our net ionic equation in these reactions will be the production of water, right? Water is a liquid, so it cannot be ions. Alright, so acetic acid is mixed with potassium hydroxide. So let's go ahead and look at this. Acetic, again, ic means 8, which means we've got acetate, right? So we've got H, C2, H3, O2, right? Because that's acetate, is mixed with potassium hydroxide. So KOH. And that yields, well, it yields what? Well, one of our products has to be water, right? So H2O. And then our other product, which has got to be what? Potassium acetate. Alright, let's have you go ahead and see. Why don't you take this reaction that I have written for you, right, that is balanced, so I don't need to do anything to it because everything was +1 and -1. But go ahead and take a minute, and I'd like you to write out the complete ionic and net ionic equation for this reaction. So let's just see how you do. So I'll give you about, let's say, 3 minutes, and let's see what you get done. All right, go. Okay, let's go ahead and take a look. So let's just start with our ions, right? So our complete ionic equation, again, is just the ions. So we've got hydrogen plus our acetate plus our potassium plus our hydroxide yields what? Again, we cannot break or dissociate the water. It's H2O because it's a liquid, plus our potassium, plus our acetate. Alright, let's look for our spectator ions. So we see potassium on both sides, we see acetate on both sides, which means all we have left over is our net ionic equation, which really is just the same thing we've already talked about, right? That hydrogen and hydroxide gives us water. And that's it. I encourage you to look back through these, maybe even take some time, maybe on your own at home, and take a look at these and just make sure you understand where each of these steps are coming from. If there's anything that you should have a question about, please don't hesitate to message me, send me a remind message, or send me a text message, even send me an email, and I'd be more than happy to get with you. Reminder that you can always come in on Thursdays and ask questions. I was there last Thursday, and I'll be there again this Thursday. Thursday to provide you with help if you need it. If there's another time that would be preferable for you, if you can get in touch with me, we can move the date from Thursdays to another day if that would help. So I do have one problem that I'm going to ask you to do, and I simply want you to attempt this. Now, key word is attempt, because this is going to be somewhat of a challenge problem. It's going to take some different concepts that we've learned throughout this year but also last year. So let's just take a look at it for a minute, and let's see how you do. So this problem is going to combine a few different things. It's going to